To tell which eye is your dominant eye, you hold up this paper with a hole in it and focus at a faraway object. I'm looking at the dangly power cord thing right now. And if you close my left eye, it's still there. If I close my right eye, the hole has shifted, so I can no longer see it, which means that my right eye is my dominant eye.
In the eye, the back surface is covered with the retina, which is a group of photoreceptors that detect light. However, all of the electrical signal from these photoreceptors has to travel out of the eye to the brain, and it does that through the optic nerve, which is right here. Your optic nerve, however, is not covered in any photoreceptors, so it creates a blind spot, which is compensated for in your brain. We can actually test where our blind spot is using the test that will follow. To test our blind spot, we use a piece of paper like this, where we focus one eye on this spot and then wait for this X to disappear. So I would cover one eye and then focus on the dark spot, and right about here I can no longer see the X. So we measure the distance from the paper to my eye, and for me that was about 15 centimeters, and so I had a blind spot at about 19 degrees. Thomas had a blind spot at about 16 degrees, and Josh around 15.
This is our test to measure the field of view of our eyes. We looked at the spot here in the center of the chalkboard, or the whiteboard. This distance is 105 centimeters. Then we walked back until we could see both edges of the whiteboard. We did this with steady binocular vision, where we kept our eyes focused here, steady monocular vision, where we kept one eye focused here, binocular vision, where we could move our eyes in our head, and when we could move our head. So these are the values we got, Josh's values, Amber's values, and my values for those four respective fields of view.
So this is the Snellen eye chart. To take this test, Thomas is standing back there at 20 feet, and he's going to read these lines. When he can no longer read, that represents an amount, so 2030, 2015. Historically, this test went like this. Thomas is the test subject, and I am Snellen's assistant. So, for example, I'm standing at 10 feet, and I can see what Thomas can see at 20 feet, which means he has better vision than me. So he is at 2010, which is better vision. Notice specific features about these letters in the Snellen eye chart. You can see they're made up of blocks that are 5 of the same size. And so when you look at the 2020 from 20 feet away, each of these little blocks would represent 1 arc minute. From our test, we determined that Josh had 20/30 in his left eye and 20/25 in his right. Amber had 20/30 in both eyes, and Thomas had 20/25 in both eyes. So this is the flicker fusion frequency test. We have a flashing LED, and we can change the frequency at which it flashes by adjusting it on the function generator. And so what we do is we see at what frequency we can no longer see the flashing. And so we tested this with a red versus green, and we saw that we had a higher value for the green. We were more sensitive to that. We also tried looking on axis versus looking not directly at it, and we saw our off axis we could see higher frequencies. That's because there are more cones off axis versus at the fovea. We tried doing this approaching the frequency from below or above, and we saw that there's a slight difference, but it's not significant. And we also tried this test at different voltages and saw that it was easier to determine the frequency at a higher voltage.
So to measure the spectral range of our eye, we used this grading monochrometer with a tungsten broadband source, and we adjusted this dial over here, which changes the wavelength, or what wavelength your eye is supposed to be seeing. It wasn't calibrated perfectly well, but we found that the shortest wavelength we could see was around 380 or 390 nanometers, and the longest one was around 770. You have to be careful because the grading, or it works on diffraction, so you can actually have multiple orders of the same wavelength, and you can see them at higher or lower wavelengths.
So this is the contrast sensitivity test. It'll show you 2 pictures, and you have to pick which one you think has the spatial frequency in it, and you just keep doing it. And eventually it should change the contrast and the spatial frequency, and you can use that data to make something like this. And the normal eye, there's like a U shape where you can see the frequencies. So this is a plot of frequency, and this is contrast.
This is a magic eye, and what it is it's a repeated image that when you actually focus beyond it with your eyes, you see sort of a pop-out 3D image. So the way I find it easiest is you hold it close to your face, kind of cross your eyes, Then you slowly let them relax, and as you pull away, you'll actually see an image